Thank you so much. Hi, everyone. My name is Marie Chatfield Rivas. My pronouns are they, them, as in, if you haven't met them yet, they work at Data.World as a software engineer, and part of their work involves building product using large language models. So today, I am here to convince you that you should all be learning less and parsing more. And the reason I believe this is that large language models are never going to be fully reliable. That's kind of the point. If they did exactly what you expected every single time, they would just return things you already knew. You want them to be a little non-deterministic. But our customers want deterministic, reliable results. So how do we give it to them? We can parse the text we get back from our large language models into well-defined values, which we can then post-process to increase the correctness. So today, I'm going to use a sample project to walk you through 3 phases of increasing complexity. We're going to start out with using standard grammars you already know. We're going to talk about how you can post-process once you have that parsed text in those standard grammars. And then we're going to talk about crafting your own domain-specific grammars. And then, because that's not enough, I'm also going to talk about some more advanced use cases, specifically how we're optimizing grammars for LLM cooperation at Data.World for some of our use cases, and how we can support multiple languages with post-processing. So it's going to be a wild ride. The project we are going to be working on today is recipes. I love recipes. This is my mother's recipe blog. She's an amazing cook. And I don't only cook recipes that my mother cooked. I also cook recipes from a lot of other different sources, and they come in very different formats. And so if you are also a cook, you love to make different recipes, you might have also heard of the Paprika Recipe Manager. This is a free plug, not sponsored. I love it. It can read basically any recipe and then turn it into structured data. And I love structured data possibly more than I love recipes. So this is great for cooking because it's all in the same place, but this wasn't enough. I needed more metadata. And then I remembered I work at a data catalog platform. We do metadata. We're built on a knowledge graph. That's kind of what we do. So I built my own custom collector to import my paprika recipes into our platform, which is normally used for things like, I don't know, databases, but I used it for my recipes. And now I have all my lovely metadata, like whether something is a hangry Monday 5 p.m. level difficulty, or if it's like a lazy Sunday difficulty. And I can search and filter for it. And every time I show this to my coworkers, they're like, that is super cool, Marie. But, there's always a but. What if you had, I don't know, ingredients? And what if you could also keep track of like which ingredients were being used in which recipes, and then you could link them all together in the knowledge graph, and then you could query them, and you could say, hey, what can I make with this thing? Because it's a graph, you can do anything with the knowledge graph. And I'm like, that's super cool. I'm a person, and I don't want to sit down and like read all of these ingredients and turn them into things in a knowledge graph. You know, and you're not going to pay me to do it, so I'm just not going to do that. Good thing for me, I also work on our large language model team, building features using generative AI. And then I was like, wait a second, if there's one thing that is really good at reading text and getting interesting things out of it, it's a large language model. So this is going to be our project today. We're going to go from ingredient text pulled out of our knowledge graph into more things we can put into our knowledge graph. So let's start out with parsing standard grammars. I, as many people do, started out by going to my favorite chatbot and said, hey, here's some ingredients. What is the list? And it gave me a list. Yeah, it was just bulleted. And sometimes it might be bulleted, sometimes it might come back with other things, but I don't want to deal with this. It has extra text. You know, so how am I actually going to get something out of here that like I can use with code so that I don't have to manually do all of this myself? I put it in JSON, JavaScript object notation. It's kind of used all over the place. Large language models have seen these a lot, especially if they've been trained on any kind of coding formats. This particular format is used all over the place for data transfer, so it's actually pretty good at just giving me back my JSON. But at this point, we still have text. I don't want text, I want things. So how do we get there? JSON.parse, right? Keyword on parse. If you have ever used JSON, you have in fact parsed things, and you know what a grammar is. Parsing is the process of going from that text that matches the JSON grammar into something. In my case, it was JavaScript objects with list of strings. But in general, a grammar is a way of explaining the rules of a language in a very formal, complex way, because computers need things explained to them exactly. So you have to say very specifically, like, JSON has to be a single element. It cannot be more than one element. And that element can have white space around it. And by the way, that value can be things that are also contain values, or it could just be like these specific things. It's very precise, right? But the thing is, like, you probably kind of already know this, even if you aren't familiar with the specific notation for it. It's kind of, if you've ever used JSON, you have some idea of what JSON is. The grammar is just the formal expression of that. And then we parse it into an abstract syntax tree. Now we're getting into the wild world of grammars and languages. So an AST specifically is referring to abstract syntax, meaning we don't really care where the commas are, we just want to know what it has in it. And a tree, it's a way of representing everything that is in our text in a way that we can manipulate and transform. And if you are at all interested in ASTs, highly recommend ASTExplorer.net. Amazing tool, absolutely love it. But here I've pasted in my JSON example, and it shows me the full AST, which does actually include some grammar-specific stuff, but also sort of what was in the text. It's a little bit more than just the simple JSON here. And if we take out all the white space, it's the exact same AST. This is the power of abstract syntax trees. They are the same, no matter the formatting. That's the whole point. It's really telling you what that text means, not just what it is. And by the way, this tool supports a lot of other languages, a ton, with a lot of different parsers. So seriously, use ASTExplorer.net. But the important thing here is that we start with some text that matches JSON grammar specifications, and we either get an AST or we get a syntax error. But once we have an AST, we can use that as some kind of data structure in one of the languages we care about. In JavaScript, this would be JSON.parse, where now we have JavaScript data structures. In Python, you get Python data structures. If you're using Java, you actually have to give it classes because Java is very precise. But you can also just return other text if you have an AST. So if you have ever used a code formatter, or prettier, or a linter or fixer in your development environment, it's because it's been taking the text that you wrote, parsing it into an AST, and then formatting that AST and spitting back a better version of what you wrote with the right spacing. Spaces instead of tabs, always. This is how I know that y'all are AI people, not software engineers. But this here is basically, this is just parsing. And it's an incredibly powerful tool. So what we're going to do is we'll generate our ingredients as JSON text using our large language model. We'll then parse it into JavaScript objects, and now we can update our knowledge graph. This is cool. So parsers convert structured text into well-defined values. This is how you're going to consistently go from something that you know what it means to something that a computer knows what it means. And if you're wondering, when should I parse text from my large language model, it's any time that you're expecting your model to return structured data. If you're just going to get raw text you're just going to show to a person, you don't need to parse that. Only if you actually want to do something with that structured data. Now that we have structured data, what else can we do with it? We can post-process it and make it more reliable. So I ran my process over and over again, and I slowly built up my ingredients knowledge graph. But sometimes I got back different names for the same thing. Like, I know, at least in my knowledge of what sugar is, that granulated sugar, refined, table, white sugar, all of these are the same thing. And I don't want 5 different things in my knowledge graph. I would rather have one thing and maybe some synonyms list. So what do I do here? Well, we could just try making a better prompt. We could embed our list of known ingredients into the prompt and say, hey, here's what we know about, and then only use these things. And if it's not on the list, you can go ahead and make a new one, but give us the most generic name. And this generally works most of the time, but not all of the time. Sometimes it doesn't do exactly what you want. or really doesn't do exactly what you want. Once again, these are generative models. They're non-deterministic. But we can write code once we have our parse values. So let's say, for example, I just have a very simple list of synonyms, and I manually update it, and every time I get back my ingredients, I check it against my synonyms list, and if I find a match, I return it. That is code that I can now unit test. That is code that I can have other people look at. That is code that every single time I give it refined sugar is now going to return granulated sugar. And if my large language model improves and returns granulated sugar on the first try, great. My code didn't need to do anything, but it's always there in case the model ever regresses. If I change my model, if I change my version, if I fine-tune something else, every single time I get back parse data that says one of these things that I know about, it's going to return the correct thing. This is why we post-process. Post-processing reliably increases the good enough target size. You just need your model to be good enough. Post-processing will take you the rest of the way. So when do you know if this is an issue that you should fix in your prompting and training versus your post-processing? If it's kind of like the main use case, yeah, fix your prompt, fix your model, train it more. If it's sort of like the main thing. But for that long trail of edge cases, known issues, no matter how many times you tell it, don't use an asterisk, and it still returns an asterisk, just post-process that. Especially if it's the kind of thing that like your model just keeps getting wrong and you can identify how to fix it with code, just fix it in code. What if things like JSON or YAML aren't good enough, or maybe you also are just a grammar and languages nerd and you want to have fun? So this is my grandmother's chocolate pie recipe. It has, in fact, garnered at least one proposal. It's a great recipe. And like many recipes that are family recipes that are actually just grabbed off the backs of different ingredients in the grocery store or out of like different cookbooks, it has a lot of brand names in it. And I did not want Argo cornstarch in my ingredients database. I wanted to know cornstarch is in my database, and Argo is a recommended brand. And I don't know, maybe I want to become a cooking influencer and start doing some like brand network deals. So it'd be really cool if instead of just having a single ingredient come back, I could know things like, are there any substitutions this recipe recommends? Are there any brands that I should probably use? And also give me a best guess if you think this is a new thing that we're creating, or if you think we've seen this before. So we could just use JSON. That's a very normal thing to do, and it's very easy. And it gives us back the correct answer. Like I said, large language models are very good at using formats they have seen before. But in my opinion, this is a lot of text to convey not a lot of data. It's a lot of tokens being used, and tokens are money. And granted, there are some things we could do. We could say, hey, like only give me the data if it exists, otherwise omit it. We could give some more complex instructions. That's all great. It will probably listen to us, sometimes maybe not. But in my case, I just wanted my own grammar because I love them. So I just said, hey, every ingredient is going to be on a new line. And the name comes first, unless you think it's a new thing. In that case, put a little exclamation mark. And then if there's any other config you want to tell me, do a pipe, and then put substitutions in angle brackets and brands in square brackets. So now this is a lot of text, a lot of meaning, and very little text. How do you teach your model about your grammar, though? Well, you could just tell it what the grammar is in the prompt every single time. This definitely works. I've had mixed results with this. With very simple grammars, absolutely great, especially if you use a known format. This is an extended Backus-Naur EBNF notation, which, once again, large language models are usually trained on a very big corpus, which usually includes formal grammar notations, which is, if you don't know this, grammars and parsers and stuff like this is like an entire field in math. It's very math heavy, it's very complex, it's been around for a while. It's kind of the best way to do things with language. This is not new. So your large language model probably knows what this is and can do stuff, but it's not a parser. It doesn't actually go and build your grammar. It's doing predictions based on what it thinks will happen next. So especially if you have a more complex grammar, it starts getting a little bit longer, or you're asking it to do multiple things at once, this kind of breaks down. You could just tell it in English what it is. Large language models are really good at logicking around English. That's kind of the whole point. So the same way that I describe my grammar to you, but maybe slightly more formally, you can just put that in a prompt. You can just say, hey, here are the rules of the grammar. And if you have some examples, like say ingredients that already exist, you can write it in that grammar, which is only going to help it give you back better results. So now we can get back our ingredients and our custom grammar, and we're gonna parse it. How are we gonna parse it? We can't just call custom parser.parse, right? Maybe you can if you use a parser generator. Parser generators are, it's just a piece of software where you define a grammar formally using a notation similar to what I showed you earlier, and it actually generates the code to turn a text into an AST, into something you can use in whatever language it's meant for. And there are parser generators for a lot of different languages with varying degrees of usability, friendliness, performance. But in general, if you have never written a lexer, a tokenizer, or a parser before, you could go learn. I had to do an entire class on those in college, but I really recommend you just use a parser generator, and if you really like it, then you can go try it yourself. But under the hood, it's just code. It's just code that's a lot better and more consistent than regex. So we're going to generate our custom grammar, and then we are going to parse it using our parser that was generated by the parser generator. And now we can actually post-process it, make sure that we're using the right synonyms, and now we can update our knowledge graph with all of these links to the ingredients and to the brands and to the substitutions until we have this giant knowledge graph of ingredients and recipes, some of which I actually did import into data.world just to prove that I could, and sort of hook it up to our lineage explorer that's really meant to be, once again, showing lineage between like tables and columns and SQL databases, but I don't care about databases, I care about recipes. So what I want you to know here is that domain-specific grammars can be more precise and concise than standard formats. It just kind of depends on your use case and your willingness to dive into the world of grammars. So should you write one yourself? Yeah, you might try it if your domain is really difficult to model in a standard format. So for example, if you are very close to but not exactly like another grammar, your large language model is probably struggling, just lie to it. Don't try to say, do leucine but slightly differently, just tell it what you want. Or if you require precise and complex syntax, so like if you're doing like 5 levels deep in JSON and have a lot of if-then rules, you might just want to do a grammar and encode a lot of that semantic into the actual format, not trying to teach a large language model about how to model it in like JSON or CSV or whatever. So that's it for the recipe part of today's description, but I'm sure you aren't actually all going to go out and generate your own recipe ingredients. You want to do things in production. So do I. I actually do like shipping code to production, not just cooking. So let's talk about a couple more complex use cases that we are actually doing today at data.world. So we have a search syntax. It's a very complicated search syntax because we have had it for a while and it has grown. And all of our customers have the ability to create their own custom metadata, which means that they can search and filter for it with their own custom attributes and values. And this means that the scope of what we support for search is very vast. So we have standard filters like status, and then we have our customer specified filters, like in this case, it might be popularity and sensitivity. In my case, it would probably be like recipe rating, recipe difficulty, any of those other things specific to the domain of the data catalog. And then we also have a way to say, I don't want to just look for a specific value in a field, I just want to know, does a value exist? Except I lied to you, that's not actually how our grammar works, because we don't go and create a brand new search syntax filter for every single possible custom value for every single customer, that would be a lot to handle in parsing. So we just have a metadata singular prefix. And then we expect that that has the actual filter, like the field name on one side and the value on the other side. But that also means that when we're doing a sort of a has lookup, we kind of need to specify, are we talking about, does it have a value in one of our standard fields or in somebody's custom metadata, just in case they also have a metadata field called status. Otherwise, how would we know which status are we talking about? And by the way, sometimes it's not human-friendly text. We show it that way in our UI, but sometimes it's actually an IRI, which in knowledge graph semantic web terms is just like a very unique way to identify a concept or a value in the knowledge graph. So this is much more precise than just random text, but we want our large language model to actually do the heavy lifting of giving us the correct, very precise value, even if under the hood, we're gonna show it to our users so it was actually the really nice label. And there's also a whole bunch of other filters in here, and some of them sound really similar, but they're not at all similar, or they do very different things. You know, we've been around for a while, we keep growing, and so does our search syntax. So I tried teaching this to a large language model, and it didn't work very well at all. It's actually pretty frustrating. I tried so many different ways of teaching this grammar to the large language model. I described it in English. I said, use our documentation, because it's been on the web for a while. I said, here's the EBNF format, and listed it in detail. It did not like it. I said, this is kind of like leucine, but it's not at all like leucine. It was putting quotations in the wrong places. It was using filters I explicitly told it not to use. It was horrible. So I lied to it. I said, this is the world you inhabit. It's the world you want to inhabit. Good thing. Here it is. You are in your happy place. You have the data as you wish the data to be. Now will you answer my question? And it did. So we basically created an intermediary grammar. We wrote a grammar that the large language model wanted to use, and then we parsed it and turned it into our actual grammar that we wanted to actually send. If you're looking at this oddly, you are not alone. Large language models also don't think that this is a good idea. But you know what? It works. It does work. Sometimes you don't actually get to just greenfield an entire thing just because the large language model doesn't like it, but you can just pretend like you did. The large language model doesn't have to know what you do in post-processing. Just fix it in post. Give the large language model what it wants based on its response patterns. So if you're at the point where you're like, I don't know, maybe I just need to like fine-tune a model on this grammar, it's really not getting it, maybe you do. But before you start fine-tuning your model, just try teaching the model a subset of your grammar. You might not need the whole thing to do the specific task you're asking the model to do in that very specific prompt. Or just give it a simpler grammar that means the same thing, or means some version of what you want that you can put into your actual output language. But I did promise you one other super fun, very exciting thing that you can do if you're really into grammars, and that's supporting multiple languages with post-processing. So as I mentioned, data.world is a data catalog built in a knowledge graph, but we also support federated and virtualized queries, which is a long way of saying that you can do absolutely wild SQL queries on our platform where you're joining a table in Snowflake, a table in Postgres, and also some spreadsheet from Google Sheets that you just uploaded into our platform in one single query and then do SQL on top of that. Wild. I have done it myself. Did not believe it would actually work, but it did. So how do we do this magic? If you guessed ASTs, you were right. That's right. We have an abstract syntax tree that we refer to as algebra. And it's basically a way of saying we can take the variant of SQL and Sparkle, which is a RDF querying language that we use to interact directly with our knowledge graph, and then we're going to turn that into a higher order abstract syntax tree. We're basically going to say, like, what does that query mean? In terms of, like, say, if you were going to explain in English what a particular SQL query does, you probably have some sense of, like, what it means that is slightly separate from the actual syntax being used, right? So that's essentially what algebra is. And then we can turn algebra into Snowflake-specific SQL or Postgres. And we can do this for only the parts of the queries that are going to each of our individual data sources. But actually, before we send it to our data sources, we optimize it. So we turn AST into better AST. This is essentially doing like code fixing on the fly. So if you write a query that's doing very silly things, we'll do better things for you. And then we transform it. So optimization, this can be things as simple as if there's a 2 + 2, just write 4. We don't need to do math every time. We know what that is. It could also be things like, hey, you just joined an entire table and then later on you filtered it, so why don't we just like filter on the join and just get a lot less data out of that database? That's a cool party trick, but if you just keep iterating over and over and over again, it ends up with a much better performing query, which really matters if you are doing these federated queries, where do you actually need to pull 10,000 rows out of Postgres if later on in the query you're filtering it down to only 5? Why don't only get 5 in the first place? So optimization is super powerful, and we can do it because we have a very powerful abstract syntax tree, so we can essentially just do math on it. We can also do these transforms. This is when we're targeting a specific SQL variant. So if we know that the database that we are targeting supports date add but not date sub, we can just do a negative date add. It's the same thing. So our users don't have to worry about like, is this one date add or date sub? They can just write whatever they want as long as we support it, and we'll target the correct database for them. So we also wanted to make it easier for people to write natural language SQL, right? This is, everybody wants it. So how did we support this? Well, we used algebra again. Turns out large language models have seen a lot of SQL, and so they're usually really good at writing the SQL that you want, but sometimes they mix and match their favorite things from different types of SQL. Sometimes they give you back stuff that just can't be run on a single system. You know, it kind of depends on your model and how it's feeling that day. So we parse whatever we get back from our large language model into algebra. We go through the same process of optimizing it, transforming it, and then we emit our version of SQL, which then, once that's in the user and they're like, yeah, I like this, go ahead and run it, it goes through the entire process the other way of going from SQL to whatever is going to query their actual data. But the lovely thing here is that if we get a syntax error, we know before the user ever sees it. And we can say, hold up there, large language model, that doesn't exist, that's completely invalid, go try again. Try again, up to however many times we want to support. So the user might see the spinner loading slightly longer, but the first time they see text, it will be correct text that runs. This is a great way to not annoy your users. Every single time you return a generated thing that does not work, that's an insult to your users. Don't insult them. So we can also add even more transforms to our library. So for example, our model loved to hallucinate schema qualifiers, and it was adding all of these extra bits of text to wherever it was trying to get schemas from that just like would not run. So instead of having to do the entire retry loop here, algebra knows all of the columns and schemas that is in this current context, because once again, at this point, we're not working in black box AI land, we are working in deterministic code that we can unit test, that we have access to our users' very specific context. So we can say, hey, that's not gonna work, I'm just gonna fix it for you, don't worry about it. And whenever a large language model does this correctly, nothing else changes, but when it does make an oopsie, we don't have to go retry the entire thing. So this entire process saves us a lot of time and gives us better output. And that is the wrong direction on the clicker. So what we can do is we can generate SQL. We can immediately say, hey, that's not a column that exists. Try again, get back a query that will actually run, parse it into algebra, format it very nicely with nice user-friendly outputs, and then this is what we give to the user. So the important thing here is that if you parse into a higher order AST, something that can represent multiple different languages or formats, you can do multilingual translations. You can go from one thing to another. You can essentially support the same set, use the same prompts, or if you've specifically trained a model on one grammar, and now you want to support a slightly different version of it, You don't have to retrain all your models. You don't have to rewrite all your prompts. As long as you can parse it into something that you can use deterministic code to translate into what you want, you can just do that all in code. Do it the cheap way. Do it the safe way. So if you're wondering, should I target a higher order AST? The answer is, if the languages you're trying to support share meaning, but they use different syntax to do that. If they don't actually mean the same thing, if you cannot write something that both of them can be parsed into without losing what they are actually trying to say, like, this is not magic. You do actually have to be able to translate it into something that still makes sense, that then you can translate into whatever you want. So, as a reminder, we talked about parsing standard grammars, how once you have parsed text, you can post-process it to improve the reliability. You can make your own domain-specific grammars if you want to have a little bit of fun. You can optimize grammars for the large language model, and you can even support multiple languages with post-processing. I hope by now I have convinced you to learn less and parse more. If you want more details, I wrote out the fuller version of these slides. They're already published on LinkedIn under my name, Marie Chatfield Rivas. It's been at the bottom of every single slide. I'll post those in the Discord. When I wrote it out, it was 6,500 words, so I split it into multiple blog posts, so you can search and skim for only the interesting bits. It has a lot more extra data, tips, and practical advice, and I will be at speaker office hours upstairs right after this. Thank you so much.